Okay, so let us start the next section, matrices. Let me start straight away with the definition and then we can discuss. Let V be an n-dimensional vector space over some field F. Then we will have a basis with n vectors. But this time, instead of simply considering a basis, we are going to consider an ordered basis. Why, that will become clear soon. Let this be an ordered basis for V over F, which means that this is not simply a set but an ordered set in which the order in which the elements, the vectors have been written, it matters. So V1 is the first element, V2 is the second element, and so on. Let T be a linear operator on V. Now note one thing. V1t, if we apply t on V1, then we get V1t. Now V1t is a vector in V again because t maps V into itself. So V1t will be a linear combination of these basis vectors. Say that linear combination is this: alpha 11 V1 plus alpha 12 V2 and so on plus alpha 1n Vn. Similarly, we can write V2t also as a linear combination of these basis vectors. So that linear combination is this: alpha 21 V1 plus alpha 22 V2 and so on plus alpha 2n Vn. And we continue like this, writing every vector on which we have applied t, that image, as a linear combination of these basis vectors with appropriate scalars. And finally, we get to Vnt, and that, according to the scheme in which we are writing these equations, this will be the linear combination alpha n1 V1 plus alpha n2 V2 and so on plus alpha nn Vn. So you can of course see the pattern in which we are writing the scalars. The scalars look like this: alpha ij, where it's a double suffix. I denotes the vector on which we are applying capital T, and j denotes the position of this scalar within the linear combination, that is Vit. For example, here we have V2t, so the first suffix will be 2 in all the alphas that appear here, and the second suffix will keep changing and will indicate the position of the suffix, the position of the scalar within this linear combination. Alpha 2 1 is the coefficient of V1, 1 here, 1 here, 2 here, 2 here, n here, n here. Okay. And now you can understand why we have said ordered basis. That's because the position of these VIs, you see, we are not changing, of course, if you want, you can rearrange the terms and write the linear combination in a different manner. Say you decide to write alpha 2 to V2 first. That you can do, but we decide not to do that. For us right now, whatever we are going to next see, for that it matters that we keep the order intact. Okay, so that's why an ordered basis. And we not only write the equations in this form, that is, first we write V1t and then V2t and then Vnt, but we also maintain the order of the original Vi's within each linear combination. Okay. Where let us also just simply mention each alpha ij, although it's understood, but it does not hurt to write that these are coming from the field. More compactly, we can write VIT. Okay, VIT is the linear combination which we can write using the summation notation as summation alpha ij Vj, where j varies from 1 to n, but the I itself also varies. For I varying from 1 through n. Alright. Note that although truly speaking, this is not how we should write a definition. In a definition, we do not, we almost never have a discussion, note that or something, but because our ultimate aim is to understand the notion and not to present something formally. So that's why I have decided to include these remarks within the definition itself. It's not exactly like a formal definition, but more like a discussion itself. Note that the n square scalars alpha ij completely determine t. Why? That's because these scalars tell us exactly what t does to every basis element. But then we also know what t does to every vector in the vector space. That's because every vector is a linear combination of the basis vectors. So knowing what t does to every basis element is enough to know what t does throughout the vector space. That's why we say that knowing the alpha ij's is enough to know t fully. They completely determine t. Okay. The matrix of t. Yeah, now it is coming. The matrix of t with respect to the ordered basis, this is this. We denote it by m of t, matrix of t, and it is the matrix that you get whose entries are these scalars in this specific manner. That is, this is the matrix. Now to enclose the entries in a matrix, you can use either square brackets or round brackets. I prefer square brackets because they do not take much horizontal space. Round brackets tend to take a bit horizontal space. But it's your own preference. You can use whatever you like. Both are allowed. Okay, so this is the matrix of T with respect to the ordered basis. Now let us see the pattern in which the entries have appeared, and that pattern is very easy. You see these equations. In the equations, you just see how the scalars are appearing. That is how they are also appearing in the matrix. For example, the equation for V1T is going to give you the first row, and the scalars will appear just like that, alpha 1 1, alpha 1 2 and so on up to alpha 1 n. That is how they are also appearing here. The second equation gives you the second row, and so on. The last equation gives you the last row. It's very straightforward. It's as if once you write the equations down in this manner, what you simply have to do is you forget the basis vectors and the plus signs, and you only concentrate on the scalars. That picture itself gives you the matrix. But here I must say something else also, which is not there in the text. Understandably, there is no need for the author to say this next thing that I am now going to say. And for that, let me just keep the equations and make some space here. Now, you know that in this text we write, although this itself has not been consistently followed by the author himself, but I have decided to consistently follow the convention that I will write the argument of a function first and the function next to that. And the matrix of a linear operator actually depends on this convention as well. In this text we are writing V1T, but in other texts, and in fact the more common notation is T of V1, T of V2 and so on. The texts where this more common notation is followed, for them actually the matrix, the associated matrix will be different. Those who are following the common function notation, for them M of T will look like this instead. The question is why? If the way we write function values also matters, then are we not unnecessarily attaching different matrices to the same thing simply because we write the, we change the notation? No, actually, this is not done simply for, it's not a whimsical decision, okay. Mathematicians have not just simply sat one day and decided, oh, okay, you write like this and you have defined matrices like this. I write like this. I use this functional notation. So for me, the matrices will be like this because I wish. No, it's not like that. There is a reason behind it. And the reason will become clear when we associate matrices to linear operators. Already we have done it, but we need to see more deeply into this association. What its consequences are that we need to see. And one of those consequences is that we will see that function composition, which is possible for linear operators also, is related to matrix multiplication in this very nice manner. Say you have two operators T and S in A of V, and you already have a basis for V. So you can then write the matrix of T and the matrix of S. Alright. Now you can of course also form the operator T composition S. For this operator also you can calculate the matrix with respect to the, see, we are not changing the basis, okay. Once we have fixed the basis, it stays like that within a discussion. So you can also calculate matrix of T composition S. Then it turns out that there is a relationship among these three matrices. The matrix of the composition turns out to be equal to the matrix of T times the matrix of S. And this relation is true only when, if we write our functional notation like this, then the associated matrix is this. Then only this relation is true. But for us, we are writing functions after writing arguments. For us, the matrix appears simply like this. Okay, because it is because of this thing that the matrix associated to the operators, for them who write the usual functional notation, they actually have to take the transpose of our matrix. You see, our row has become their column, and their rows are our columns. And this is one of the advantages of using this somewhat less common notation for writing function values. The other advantage also we have already talked about. The other advantage is more simple. If you have two functions, say f from set A to set B and g from set B to set C, then in the more common notation, the possible composition is G composition F. Why? That's because they write arguments to the right of the function. So they can apply F first and then on Fx they apply G, which makes sense because first we apply F to the elements of A, that takes us to B, and then on those images we apply G, and that takes us to C. However, you see, they had to change the order. Although F is being applied first and then G, but they cannot write F and G. That won't make sense because the object on which they are applying these things that lie to that side. However, for us, this same thing we can write keeping the order of the functions intact. If first we apply F and then G, we write F first and then G. Okay, we do not need to change the order. So this is the more simple reason for using this notation, but this is another reason. But anyway, we do not actually have to bother about this because we will keep writing, right? We will keep using this notation. This notation is used mainly by algebraists. Other mathematicians use the more common notation. There are other notations also. For example, the same thing some people will write like this: V1 superscript T, but let's just not discuss about those things. They are not necessary to us. Okay. Now, what consequences can there possibly be of this association between linear operators and matrices? That is our aim. next in. We want to see how deep this association takes us. But before we do anything else though, we start proving theorems or anything, we first should see some examples. So the first example, in fact this is the only example we are going to see today. It is about this space. Let F be a field and V be the space of all polynomials of degree at most n minus 1, where n is some positive integer. Okay. That I am not writing, the author also has not written it explicitly. In fact, Herstein is known for not bothering about such small things, which sometimes causes problem. But this, let's just assume that n is greater than or equal to 1, so that n minus 1 is at least 0. Okay. Along with the 0 polynomial over F. So what does V consist of? The elements in V are polynomials over F of degree at most n minus 1. But because the 0 polynomial has no degree, so we had to separately say along with the 0 polynomial, otherwise V will lack a 0 vector. Then it won't be a vector space. So that means the general element of V will look like this. The general element of V will look like this. Beta naught plus beta 1x plus beta 2x square and so on plus beta n minus 1 x to the power n minus 1, where these beta i's are elements of the field F. On this vector space, we are now going to define a linear operator. Consider the function d from D to itself, whose under which the image of this element x square plus so on that is this is beta 1 plus 2 beta 2x plus 3 beta 3x square and so on. You know what we are doing here? It's actually nothing but the differentiation operator. Verify that D is actually a linear operator on V. That is, D belongs to the algebra A of V. I mean to the vector space A of V. I should not perhaps say algebra. I mean the algebra aspect of this we will see, but let's just treat this as a vector space for now. Okay, so this is left to you. Please go through the details that D is a linear operator. So D respects addition and scalar multiplication. You need to show this. It's absolutely straightforward, but still you go through the details and see that you can actually write down the thing fully. Okay. Now consider the basis, or rather I should say the ordered basis Looking at the structure of the general element in V, it's not difficult to see that these monomials form a basis for V, and say we have decided to take the vectors in this order, in this quite natural order for V over F. Note that we know what V is, but F we haven't specified. F is any field. F may actually have only two elements, 0 and 1. That is also possible. Alright. Now let's try to calculate the matrix of D with respect to this ordered basis. For that we need to first know those equations. What we get when we apply D to the elements of this basis to these vectors in the given order. So we start by applying D on 1. We have 1D. You see, no need to remember this definition exactly like what is given. You just remember that D is the differentiation operator. That's it. And then you use your ordinary things that you know from calculus. So this is 0. By definition also it is 0, and actually we also know that it becomes 0 because 1 is constant. Although I should again repeat one thing which we have already discussed in field theory. You see, although this is the differentiation operator, but it's not exactly the limit of anything. That's because the underlying field is not necessarily the field of real numbers or the field of complex numbers. That's why I said just now that F can be a finite field also. So in such fields we do not normally have any natural topology or anything that you can use to define D as a limit of something. It is just defined using the form in which we should have the the derivative polynomial. Although we call it the differentiation operator, but it just has been defined following the same pattern that the actual differentiation operator follows. That's just it, okay. And because of that, following that same pattern, some of the properties of the actual differentiation operator from calculus also are true here, but that does not mean that they are the same thing. We are not getting 0 here because the derivative of a constant is 0, but because the definition gives me 0, that is why. But anyway, so if you now start writing the 0 as a linear combination of these basis vectors in that same order, you get this. All the coefficients have to be 0. Okay. Next, xd. xd is 1, so this becomes 1 plus 0x square and so on 0x to the power n minus 1. Let us write one more, x square d, that is 2x. So that is 1 plus 2x plus 0x square plus 0x to the power n minus 1. And we continue like this. Eventually, finally we apply d on x to the power n minus 1. That by the definition is n minus 1 times x to the power n minus 2, which is 0 plus, that is 0 times 1 plus 0x plus 0x square and so on, and n minus 1 x to the power n minus 2 plus do not forget there is one more, 0 x to the power n minus 1. So now we can write the matrix. Now writing the matrix, we will get this. So let us call this matrix M1T, because we are going to consider two more bases and write the matrices of M1D. Two more bases are going to be considered, for which also we are going to write the matrices for D. So those matrices we will call M2 and M3. That's why we are writing M1, although we could have simply written M. So what is the first row? The first row will consist of these zeros only. Okay. In the second row, the first scalar is 1 and the others are 0. In the third row, the second scalar is 2 and others are 0. And it will go like this. It's a kind of a diagonal. In the row below that, in the fourth row, you can guess that the scalars will come in this pattern 0, 0, 3, 0, 0, 0 and so on. All the others are 0, which we do not write. Okay, how many more shall we write? And finally, this scalar is only the non-zero one. Non-zero one means it is not exactly equal to 0. It may or may not be 0. We don't know. So it will appear where? It will appear in the column corresponding to x to the power n minus 2. That means this one, the penultimate column. So the scalars, the non-zero scalars that are appearing in this, along this diagonal, will end here, and the others are 0. Okay, so this is the matrix of the differentiation operator with respect to that ordered basis, which seems very natural one. But we can change the order also, and instead consider this basis. Say we change the order and take the completely reverse order. The vectors are the same, but we change the order, and because of that the basis actually has changed. The ordinary basis has not changed, but the ordered basis has changed. Now what possible change will you see in the matrix if you calculate the matrix for this ordered basis? Instead of blindly guessing, let's just write the equations. You may think that nothing much will change, but let's see. X to the power n minus 2, and now you are supposed to write this as a linear combination of the basis elements, but maintaining this order, okay, not that order. So first of all, you have to write x to the power n minus 1, that is 0x to the power n minus 1, and then this one will come. n minus 2 plus, let's write one more, n minus 3 plus 0x square plus 0x plus 0, 1. Then let us write one more, n minus 2d. So this will be n minus 2 times x to the power n minus 3. And when we write that as a linear combination, we get this n minus 2 plus n minus 2 times x to the power n minus 3 plus the others will be 0. You understand that, okay? So I am just simply writing like this, not writing the x square term. And like that, if we continue, finally what shall we get? How many more shall we show? Okay, so let me calculate this. This of course is 2x. Expressing that as a linear combination plus 2x plus 0, 1. Then xd is 1. Zero x square plus 0x plus 1, 1. But there is one more, do not forget this. This was the first one there in the previous ordered basis. And here of course everything is 0. Okay, now let's write the matrix. Can we manage the matrix here? I think we can. Let me denote it by M2D. So because we have decided to show how many vectors, we have also actually shown this one as well, not here but in these calculations. So there will be 1, 2, 3, 4, 5, 6 columns. And how many rows? 1, 2, 3, 4, 5, along with the intermediate row consisting of those dots. 6 rows and 6 columns. So the first row has the first element 0 and then n minus 1 and then the others 0. So 0, n minus 1, 0, 0, 0, 0. Then in the second row, the first two are 0, then n minus 2. 0, 0, n minus 2 and then everything else is 0. And then dots. Put the dots also nicely, okay. Whenever you put dots like this, okay, whether it is horizontal dot or vertical dot or diagonal dot, use only 3 dots, not more, not less. This is the rule. 1, 2, 3, 1, 2, 3, 1, 2, 3. Then we come to x square d. Here we have almost everything 0, only this one is non-zero and that is 2, then 0 and the others are 0. See, while writing this kind of things, we can easily make mistakes. Do not write dot 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 here. Why? Because you do not have anything here in between these two zeros. Here we have dot because we have not written the other intermediate columns. But here you have column and the very previous column is this itself. So no dots will appear here. But in a frenzy of writing dots, we may end up writing dots here as well. That is also a mistake. Okay, then xd. So xd will be 0, 0, 0, 0, 0, 1. And there is one more row which corresponds to 1d where everything is 0. So you see that the matrix of that same differentiation operator with respect to this new ordered basis is quite different from that one, okay, the previous one. Also, note one more thing, that the original vectors were also present in the previous basis, only the order has changed. Just that alone has changed the matrix significantly. Okay, so that is why order is very important. But there is, of course, there are infinitely many bases, but there is one more the author has considered of the same space. Let's see that one also. And that basis, this last one is, I think he has added one, yes. Except that one which is also present in the other bases, with the other vectors, other monomials, Herstein has added 1. And he has asked us to, or he has simply remarked that it can be easily proved that this is also a basis for our space. How? To show that simply, you see, we already know that our space is n-dimensional. From the previous basis itself, that becomes clear. So here also we see that there are n vectors which are clearly distinct, okay, no two of which are equal. Now if we can show that this set is linearly independent, using the following procedure, how we show a set is linearly independent. You take a linear combination of these vectors, set that equal to 0 and prove that the coefficients are all 0. You then get a set of n linearly independent vectors in an n-dimensional space. So from vector space theory results, this will be a basis because it will then necessarily span the space as well. So that's how you can show that this is the basis. In fact, this is also something I would ask you to do on your own. But let us now see the matrix of D with respect to this basis. I am not going to go through the calculations, okay, I will just write down the matrix. You can do the calculation. In this case, the matrix turns out to be this. You can expect that here, because the vectors also have changed from the previous two bases, not just the order. So the entries will significantly change, and that is the case. So here the matrix looks like this. Here also first 3 columns followed by last 2 columns. Okay. And then in the next row we have 1, 0, 0, 0, 0. But then in the next one we have 2 minus 2, 3, 0, minus 3. It's like these two entries are balancing each other. That's a way of remembering this matrix. But they are going further and further apart. The more we go, I mean from top to bottom, they become more and more separated. And like that, if you continue, the last row will look like this: minus n minus 1, 0, 0, and n minus 1 will appear in the penultimate column, the column before the last one, followed by 0. This is the matrix with respect to this new ordered basis. So this is also a kind of homework for you to verify that this is actually the matrix of D with respect to the ordered basis. In this, for this matrix, in its calculation, simply calculating the D values of these vectors, these polynomials, won't be enough. When you try to write that D value as a linear combination of the basis vectors, you may need to actually do some calculations. It won't come as quickly as these other cases, okay, these previous two cases. But that's it, that you have to do it, okay. You will see that you are getting this matrix. Now, note that we have got three quite different matrices: M1D, M2D, and M3D. And we can expect to get different matrices if we keep changing the ordered basis. Simply changing the order of the vectors itself has caused significant difference in the matrix. But in spite of all these differences, we still feel that because these are all matrices related to D, somehow they themselves are related on a more fundamental level. As matrices themselves, they are somehow related. And yes, they are related. However, the relationship will have to wait. We still have some time to see the actual relationship. Now, let me end the video by drawing our attention to something we have already seen when we were discussing characteristic roots. You remember, we have already proved that for an operator on an n-dimensional vector space, there are at most n characteristic roots of the operator in the underlying field. And we have already considered a special case in which those n roots are all distinct. Let's consider that again. I can write here itself, let V be n-dimensional over F. Because we are discussing vector space, so no need to write that again. Let T be a linear operator on V, and let such an operator have n distinct characteristic roots, lambda 1, lambda 2, and so on, lambda n in F. Then a previous result tells us that the vector space has a basis for it consisting of characteristic vectors corresponding to these characteristic roots. And that result is corollary 2 to theorem 623. 62 means the previous section, by corollary 2 to theorem 623. V has a basis V1, V2 and so on up to Vn such that Vit is equal to lambda I Vi. That is, Vi is a characteristic vector of T belonging to the characteristic root lambda I for all the i's. Okay. Now if one tries to find the matrix of T with respect to this ordered basis, say we try to find it, what shall we get? Let's see. Are we going to get something special? Yes. So what is V1T? V1T is lambda 1 V1. So if you write it as a linear combination of these basis vectors maintaining order and everything, then it looks like this. Lambda 1 V1 plus 0 V2 etc. plus 0 Vn. Then the next one, V2T is lambda 2 V2, which is 0 V1 plus lambda 2 V2 and so on. The others have 0 coefficients, 0 Vn. Continuing like this, finally we get Vnt, which is lambda n Vn. 0 V1 plus 0 V2 and so on, finally lambda n Vn. So now if you write the matrix of this operator, then the matrix is especially easy. The matrix will be a diagonal matrix. I am using these terms because we already know about matrices even from our school days. There was one point where matrices were not introduced in school, but nowadays we see matrices for quite some time in school itself. So we know about these things, diagonal matrices, scalar matrices, matrix addition, multiplication, these things we already know. Okay, so the matrix of T will be what? The first row, of course, is this. The second row is this. And the third row you can imagine will be 0, 0, lambda 3 and the others are 0. And the final row is this. So this is a diagonal matrix. And diagonal matrices are very easy to handle. There are many reasons to consider diagonal matrices. They are already pretty simple, but there are some even simpler matrices which are scalar matrices, diagonal matrices whose diagonal entries are all equal, but that is just too much simplicity. This is kind of a non-trivial simplicity. You already know why diagonal matrices are simple. For example, you can multiply two diagonal matrices simply by multiplying their corresponding diagonal entries. That's it. That is also going to be a diagonal matrix. Inverses of diagonal matrices which are invertible can be found simply by taking reciprocals of the diagonal entries. So they are that simple. So we will see that this association between operators and matrices can be used to know things about operators without actually working directly with operators themselves, but working with their corresponding matrices. And that's why we want to be able to find a basis with respect to which the matrix of an operator is very simple like this. That unfortunately and realistically, of course, is not always possible, but we try to find bases for a vector space so that the matrix of our operator with respect to that basis is as simple as we can possibly get. So this is a general thing, and this will give us many things. So let me just end the video here itself. So we will see after this what comes next, and we are yet to see more about this association. Okay, how it is that we can simply work with matrices and still know about operators. We have only linked the operators with matrices, but we have to link the operations as well. You will see that in a very nice manner, addition of two operators corresponds to matrix addition. Multiplication of multiplication of operators actually is their composition. That corresponds to matrix multiplication, and in fact, this is how the definition of matrix multiplication comes. And this association takes us very far and very deep. So that's just it for tonight. See you in the next upload. Until then, this is me, Lucifer, from A Mathematical Group. Have a nice night.